This lesson is going to be about a new set operation called the Cartesian product. It's really useful whenever you want to combine more than one set. We would use the Cartesian product anytime we wanted to pair elements between two sets. So to give you the first example, imagine you were at a dance and you had a bunch of dancers. On the left you had the male dancers and on the right you had the female dancers. One thing you could do at the dance is you could pair a male dancer with a female dancer, like this. Another thing that you might want to do is you might want to pair some foods with a drink. So for example, I could pair a burger with cola, and then I could pair chips with lemonade. Or maybe you have a group of people employed at some shop, and you wanted to choose one of them to be the manager, one of them to be the assistant, and one of them to be the owner. Either way, anytime you want to pair elements between two sets, you're going to need to use the Cartesian product to do this in some way. So without further ado, let me actually show you another set, and I'll actually show you what the Cartesian product of that set looks like. I want you to imagine that I woke up one morning and I looked in my wardrobe. Inside my wardrobe, I had a set of shirts and I had a set of pants. I want you to notice that I had 3 different shirts and I had 2 different pairs of pants. Now the Cartesian product of these 2 sets is going to produce every single possible pair of shirts and pants. The Cartesian product is usually written with this multiplication symbol. It takes in 2 different sets, and then it finds every possible pairing of the elements in the first set and the second set. Now remember that sets do not have an order. So I'm going to choose at random to wear a yellow shirt and black pants. So the Cartesian product set here just contains every single possible pairing of shirts and pants, where the shirts come first. Now the reason we call it a product is because we have 3 shirts and 2 pairs of pants. So that means we're going to end up with 6 possible pairings, as you're about to see. Okay, so as you can see, over here we have exactly 6 possible pairings of shirts and pants. If you look carefully, the first row has black pants and the second row has blue pants. The first column has yellow shirts, then we have purple shirts, then we have green shirts. You also might be wondering why I've put brackets and commas on everything. We call these things tuples, and they're useful to help us organize information in an ordered way. You can almost think of them like sets, but ordered sets instead. So in a sense, order actually matters for one of these tuples. If you change the order, you actually end up with something completely different. So therefore, the purpose of the Cartesian product of 2 different sets is to write out every possible pairing of the elements in these 2 original sets. Now, one of the reasons we call it the product is because it multiplies the cardinalities of the original sets. For example, this set had a cardinality of 3, this had a cardinality of 2. 2 times 3, or 3 times 2, is the same thing as 6. Unlike multiplication, however, the Cartesian product does care about order. If we did P times S, then what we'd find is that the pants would come first, and then the shirts would come second. Whereas, as you can see in this case, S times P puts the shirts first, followed by the pants second. Now this is actually really useful, because it allows me to list out every possible outfit that I could wear on a particular day. Having a list of every possible outfit is actually pretty useful if I want to solve problems regarding what outfit I'm likely to wear, for example. Like, I might be more likely to wear this than I am to wear this. But aside from just taking the Cartesian product of 2 different sets like this, it's also possible to take the Cartesian product of some set with itself. If I take the Cartesian product of the set of pants with itself, I'll end up with this new set over here, which is going to be P times P. Just like we do for multiplication, we're going to also write this as P squared. So to construct this new set over here, we just take a pair of pants from the first set first, and then from the second set second. And then we want every pair of pants where you took one from the first, then one from the second. The exact same rules apply to the Cartesian product of the same set as would apply to these Cartesian products up here. You end up with a set of exactly 4 tuples, because that's the same thing as 2 times 2. And the order of the pants in each tuple actually matters, because if you have them in an opposite order, it may mean something different. For example, the first pair of pants could represent what I wore yesterday, and this pair could represent what I wore today. And you can see that black pants yesterday and blue pants today is not the same thing as blue pants yesterday and black pants today. So that's why we say that order is important in tuples. They're kind of like sets, but order is important, and you can actually have repeated elements. And those two things you cannot have with sets. So to distinguish coordinates or tuples from sets, we write them with these round brackets, instead of those curly brackets that we use for sets. So now that you roughly understand what the Cartesian product is, let's go ahead and actually find the Cartesian products of some explicitly written sets. Okay, so I've defined 2 sets, A and B. The first set contains the letter A and the letter B, whereas the second set contains the numbers 1, 2, and 3. I'd like you to find the Cartesian products, A times B times A, and A times A. You can pause now if you like to try it yourself. Okay, so to find the product A times B, I'm going to start by writing out the new set that we're going to place all of the tuples in. Now, to find the Cartesian product, I like to imagine an imaginary grid running along this new set. I want you to imagine that the first row contains all of the A's, and the second row contains all of the B's. Then the first column contains 1, then 2, then 3. Okay, now since A comes first, you're going to take your items from this set first. So that means the first element is going to have an A over here and a 1 over here. So this is going to be the coordinate A1. Now the whole first row has A's in it, so the next coordinate is going to be A2 and then A3. I want you to notice that the things we're putting in our new set are actually coordinates. Now we've finished the row of A's, but now we should do the row of B's. We're going to copy these exact same things, but replace all of the A's for B's. Now this means that this set over here is the resulting Cartesian product A times B. Now as I said, the set B times A is not going to be the same thing as the set A times B. They're going to be very similar, but the only difference is going to be the order in which the sub-elements appear in each tuple. However, as far as the cardinality is concerned, I want you to realize that 2 times 3 is the same thing as 3 times 2, so you're still going to end up with 6 elements, and they're going to be the same elements, but as I said, the only difference is going to be the order. So let me go ahead and start by copying out the exact same markings that we had above. For this first element, we're still going to take A and 1, but this time we're going to take the element from B first, and 1 is actually the element that shows up in B. So that means the coordinate here is going to be the coordinate 1A. Now similarly, the next coordinate here is going to be the coordinate 2A, and then you're going to have 3A, and so on. So as we said before, changing the order of the sets in the Cartesian product does not change the elements, but it does change the order in which the sub-elements appear in each tuple. So now let's turn our attention to this last case. Now if we wanted the Cartesian product of A with itself, then we better do the exact same thing we did here, but instead of having 1, 2, 3 as the columns, we'll have A and B again. I'm going to assume that the row tells us the first letter, and the column tells us the second letter. That means the top left-hand corner is going to contain AA. And then this term over here will be AB. Then after this, you've also got BA and BB. Now I purposefully picked sets that were very similar to the sets we started with here. I want you to notice that we have a set of 3 and a set of 2, just like we had over here. In fact, if you swap purple shirt for 1, and then yellow shirt for 2, and then you did black pants for A, and so on, then I want you to notice that this set you ended up with here is identical to these sets you ended up with over here. And then the same thing holds true for A times A, which looks exactly like P times P. we can call a times a squared. Just remember that. Now you can take the Cartesian product of two sets no matter how large they are. But as you should hopefully realize by now, it's going to get very, very long as you get more and more elements, because after all, you are multiplying the cardinalities. But this just about completes our example, so I'm just going to say one more thing before ending this lesson. Now just like you can multiply more than two numbers, you can also take the Cartesian product of more than two sets. So let me start by bringing back the set of shirts and pants, and then we'll add one more set on, just to show you what we can do. Now let's suppose that aside from picking a nice shirt and a nice pair of pants, I also wanted some footwear to go along with my outfit. And inside my wardrobe, I find two pairs of shoes. I'm not really sure which one actually looks better. I have this really nice pair of shoes here, and then I have this also really nice pair of shoes here. By adding footwear to the mix, we've actually doubled the number of possible outfits that we can have. For example, I could wear this purple shirt, this black pair of pants, and this blue pair of Crocs. I think this might just be the most beautiful outfit in the world. Or maybe I can choose to leave the house in a much less sensible outfit. Like I could wear this yellow shirt, this pair of jeans, and these not as nice shoes. This new set over here is going to be the Cartesian product of the sets S, P, and F. Now since we have 3 shirts and 2 pairs of pants, then in total we're going to have 6 possible pairings of shirts and pants. But because we have 2 different pieces of footwear, that's going to further multiply the number of elements by 2. And that means that the cardinality of this set over here must be equal to 12. Now there are other outfits that I could wear, but I haven't drawn them on, because after all, I'm like 99% sure that I'm going to walk out with this one. But I guess the main point that I'm trying to make here is that you can take the Cartesian product of more than 2 sets if you like. The only difference will be that if you take the Cartesian product of 3 sets, then the tuples in your resulting set will have 3 elements in each of them. But even when you do this, it's still true that you just multiply the cardinalities to get the cardinality of the resulting set. And the order does still matter. For example, if you did F times S times P, then you put the footwear first, then the shirt, then the pair of pants. You'd still get the same elements, but they'd be in a different order. And that just about completes everything we wanted to say about the Cartesian product. So let's summarize. The Cartesian product contains every possible pair of elements in 2 sets. When you take the Cartesian product of 2 sets, you make new elements from those 2 sets by actually making tuples of the elements in each set. The Cartesian product will end up with every single possible pairing of elements from the first set and the second set, with the first set first and the second set second. It's perfectly possible to take the Cartesian product of a set with itself to get something like this. And it's perfectly possible to take the Cartesian product of more than 2 sets, if you like. No matter what, the cardinality of the new set that you've created from the Cartesian product will just be the product of the cardinalities of each individual set. Now most of the sets I've been dealing with here stayed away from real numbers, and we definitely stayed away from infinite sets because it would take way too long to write them all out. But actually, the Cartesian product becomes much more useful when you actually use it for infinite sets and for sets that contain numbers. That's something I'm going to show you in the next lesson. But for now, I'd like to complete our lesson on the Cartesian product. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.